I think we should get started. So, Welcome everyone for today's session. I am Ayush Kumar Tyagi. I am PhD student at IIT Delhi. I work in intersection of medical images and computer vision. In today's session, we will be looking into autoencoders, and major part of it will be focused on transformers and the applications like machine translation, uh, captioning, and all. Right, we will in the coding part we will look into variational autoencoder, which is a variant of autoencoders, and see what applications we can use based on that, right? And the second part will be focused on implementing a transformer architecture from scratch, and we will see various component dimensions and how does the overall architecture looks like. So we should get started. Okay. um, so first question is about denoising autoencoder. So for a recap, what does the autoencoder look like? So there are basically two parts to autoencoder. So you have encoder, you have decoder. For an input x, we are basically predicting x hat, and we are trying to minimize the distance between x and x hat, right? This is MSC objective we are trying to minimize, and there is a intermediate representation which we called as the latent space slash representation, right? There are variation of this. There is something called the variational autoencoder, which bounds this latent space to be normal Gaussian, right? So that it become easier for us to sample. And there is a theory about it, how do you actually convert autoencoder into a variational autoencoder. There is something called the elbow and lower bound. So that is actually an interesting read. So if you want, you can actually go and read about that. In denoising autoencoder, what is happening here is we have an image with some sort of a noise, right? And the objective is to basically remove this noise and get the original representation or the original image in our case, right? So what the question is asking here is, given an input dataset x, can the encoder of denoising autoencoder learn many to one mapping from x to x, right? So many to one mapping is like you can have multiple inputs, and you can have all of them should be mapped to similar representation, right? Suppose if there is in the data set there are different type of noise, so maybe salt and pepper noise, even the Gaussian noise. So I can actually have an encoder which is able to eliminate all these type of noise and like and convert that uh, image into a unique representation, right? So it so the answer is basically yes, it can learn uh, many to one mapping, and it should be able to basically uh, uh, map it to a unique representation, right? So this is what it is doing. So like this there is another variation of autoencoder, uh, which is over complete autoencoder, where instead of like we are reducing the dimensionality of the input, in that case what you're doing is like the latent representation is actually greater than what uh, your input dimension is. So it is called as actually the sparse autoencoder. And then basically we expand the dimension and then we shrink it to the original dimension. So there are many variants of these autoencoders, and it is actually very interesting read to go about. And hmm, I think that should be fine. Since we are talking about autoencoders, I think it's good actually to see uh, the code as well. So I think let's change the structure this time. So we will uh, see, solve a problem and see if we can actually connect it. Uh, so let me just share my screen. So this is this is the code actually, uh, right? So of variational autoencoder, and what I'm doing here is I'm using a simple data set for which is like MNS data set, which we have seen earlier as well. So for CNN based applications like classification task, right? And what I'm trying to do here is I'm trying to learn the reconstruction part, where I'll feed in any image and it should output the same image. Then what I'll do is like I'll start to use the latent space to generate new samples which are not there in the original data sets. So like for an autoencoder we can actually use it in different ways, right? So there is let me see. So there can be different application of the same task, right? So autoencoder we can actually use to learn representation. So, and second is basically generative tasks. So in both the cases, these are basically the byproduct of whatever the training we will do, right? I hope you can see my iPad. Okay, great. So what we'll do is like the first step is we train an autoencoder, right? You have image, you are basically trying to predict out images, and you have a latent representation, latent vector or latent representation of this X as well, right? So so you have learned a representation of X. So now instead I can simply throw out like your original data, right? And whenever I want I can actually store this information, this uh, information about that X image in this maybe suppose this is 64 dimension vector. So I'll just store this 64 dimension vector, and I have all the information about what was there in the image. And whenever the time comes, suppose I want to see what was there in the image, I'll just use this decoder, pass this image or this vector to the decoder, and it will basically generate it will try to reconstruct the original image, right? So in term of storage, people actually store these representations only instead of storing the whole image because of the space constraint. In the problems like facial recognition, right? So you don't want uh, to store whole images, right? So people extract out features and only store the feature vector. And whenever you are basically a new phase arise, right, you extract out feature of that phase, and you have a whole data set of all the faces and which are stored in a form of a vector, and uh, you just compare the similarity between the new face and whatever is there in the your database, and see if it matches. And this comparison is actually happening at the latent space or the lower dimensional space, so it is basically faster and actually computationally efficient. So this is the task of learning representation. So for an image, you can use autoencoder to learn a representation of it and use it on various downstream tasks. Another downstream task can be like, suppose um like you want a good representations for a classification task. So suppose you have trained the autoencoder. What you'll do is, like, you just, for any image, you just pass it through encoder and take this latent representation, and then just simply pass this latent representation to one or two layer of neural network and do a classification task, right? Because since you have trained autoencoder, these representations actually contain good representation of whatever your the image contains, right? So that actually becomes very helpful, so you don't have to start train everything from scratch. For generative task, what we'll do is, like, you'll uh, like maybe sample from suppose some distribution, a 64 dimensional vector, and pass this 64 dimensional vector from to a decoder, and this decoder should be able to generate you some image, right? Closer the sampling is to the original distribution, the closer it is for uh, um, the more realistic images the decoder will generate, right? And right now this if you might see this chat gpt or other generative models, so what they're doing is, like, they're actually uh, doing similar task, but like you have text information, right? You create it to in some sort of embedding. This embedding you give it to uh, some generative model, which is essentially a decoder, and then it generates you the overall the new image, right? And if you say, you can actually do editing as well in the original image, and whatnot. But and thing the whole thing has actually many applications, and it's very useful. So we will actually look into one of the variant of this autoencoder, which is variational autoencoder, because it restricts this latent space. So this latent space actually become 0 1. So it's a normal distribution with zero mean and unit variance, right? So now I have a limited space to sample from, and within this limited space I should be able to generate good samples. So we will see, like, how good samples we are able to generate, and how do you actually visualize the whole learned space by perturbing um, the sampling actually. So let us see in the coding part. uh, okay, so this is the code for variation not encoder. So what I've done is I've imported whatever the essential libraries are required, right? And whenever you are running, just run it using change runtime and use this GPU, T4 GPU to run the code, so it becomes actually faster. So for data loader, for data I'm using MNS data, and out of MNS data I'm only using 1, 4, and 8 digits. I'm not using all the digits for simplicity, right? So what I have done is, so this data set, like MNS data set, is already there in the torch vision class. So you simply need to write dataset dot mnist root dot slash data, and this train is equal to true actually. uh, just downloads your training data, and train is equal to false, download your test data. And for this what I have done is I have I've only subset like labels basic 1, 4, and 8, right? And this is the uh, class which is basically subsetting that labels. So there are labels from 0 to there are digits basically from 0 to 9, and I'm using only 1, 4, and 8 in this case, right? And this data subset I actually pass to my data loader, which actually fetches this data in a batch of whatever the batch size I define. So for training, the shuffle is true. That means that like I'm shuffling the data while I'm fetching, right? This is the overall class of variation auto encoder. You have a encoder, you have a decoder, and it's a very simple encoder decoder architecture where you have a like linear layer. So what I'm doing is, like, for each image I'm just flattening it out to a dimension of 784 dimension, right, and a hidden dimension of 400, right, and I have a latent dimension of 2 in this case, right? So what I've done is I have input which is coming from 784. I have mapped it to 400 dimension, and from 400 dimension I am actually mapping it to 2 dimensional vector. So our latent vector is basically 2 dimension. And for variational autoencoder you need mu and sigma. So let let's not go into detail, but just see that, like, instead of directly predicting the latent vector, what they do is, like, they predict a latent mu and sigma, and using mu and sigma they actually compute the final latent vector, right? And the decoder, it takes the latent dimension 2, map it to hidden dimension, that is 400, then hidden dimension map it to the original image dimension, that is 784, right? So you have this encoder block, um, right? And so this is something called as the reparameterization trick, where you add the mu with with the standard deviation, and there is some randomness too. So mu plus epsilon sigma, basically your standard deviation plus some epsilon, right? uh, and In forward pass, what is happening here is, so you have the input image which is coming. I am predicting mu and variance. uh, I'm using reparameterization to basically get me the whole latent vector. I'm passing this latent vector to the decoder, and it is basically generating me, it was basically returning me the whole image, The loss function for bidirectional autoencoder, there are two like loss function. One is the KL divergence, and the other one is basically you can actually use mean square error as well. Since but this was the binary output. Images are like binary in this case, either 0 or 1. So I can actually use binary cross entropy as well. And KL divergence is what is between whatever we are predicting and unit normal actually, which we have seen. Yeah, and then this is the training loop. uh, you're basically fetching data from train loader. The model is basically giving you reconstruction, uh, right? So whatever input I'm giving, I want that to be reconstructed in the autoencoder, and based on how good the reconstruction is, I can see that whether we are basically training or not. You have the intermediate representation as well, mu and sigma, and you compute the loss function, you do loss dot backward, and then optimizer dot step actually updates your weights, right? So I train it for 200 epochs. I use Adam optimizer for this with a learning rate of 1 e minus 3, right? So this is the reconstruction. So first row is basically my input. So this is 1, right, and this is 5, and the last second uh, row is basically what my model is actually reconstructing. So I'm passing 1 as an input, and model is actually able to reconstruct the same image in the output, right? Right, so now in case of learning representation part, I can just feed this image to encoder and get my latent representation, store the latent representation, and I can actually throw away whatever the original image was. So there are many applications which I can deal with using this by storing only the latent representation of this image. Next, what we are actually doing here is we are basically perturbing um, the latent representation. So what I am done is I am just um, like slightly adding some noise to whatever my whatever the latent representation was. So for this 4, right, I am adding some noise, and see what kind of reconstruction is happening. So if I perturb it with -2, right, so it is actually the 4 becomes 1. If I perturb it with -1.20, it becomes 8, right, and if I perturb it with 4, it actually remains same. So even in some cases in the perturbation, the, the reconstruction actually become uh, like bad, right? So at because model has not seen at that point uh, what was the mapping, right? So it tries its best, but it becomes difficult. So I don't so this is actually the whole manifold look like. So we at suppose this is 0 0, right, and if you start moving, so there are two latent dimension, right? Like so there is one at 0th place, and there is a one at the unit place, right? Sorry, the next place. So suppose perturbation on 0th place is shown along this axis, x-axis, and the perturbation along the second place is shown along this axis. So if I start adding some uh, like numbers to whatever my the latent representation is, it starts to generate different type of numbers, right? So this is basically the generative task. So what I am here doing here is um, I am basically sampling. I am creating a Z sample. This is for from whatever, like, so minus um, like from 0.05 to 0.95 along x-axis, and point 0.5 0.05 to 0.95 along y-axis. So I have created a grid of x and y, right? And I'm using this x and y as my latent vector, right? And I'm passing this latent vector to my decoder, and this decoder is generating me a image, right? And if you actually see at uh, this is at point zero 0.05 comma point zero 0.05. So this is at point zero 0.05 comma point zero 0.05, and it is generating 0, right? And if I am actually moving from point zero 0.05 to maybe point 10 comma like point zero 0.05, then it is still 0. But if you can actually see, we are moving from 0 to 5, right? So as I am moving from along the horizontal axis, I am actually able to see a different generation pattern from my variational autoencoder. And simply along the y-axis you can see different type of patterns. So if you can see that, like, this region was uh, dedicated to generating 0, any point that comes from this latent space will actually map it to 0. Along the center you can see that um, any point which is coming from this region will be mapped to 5, and anything that is coming from this region will map to 1. So this is basically your manifold. So this is the space you call like the latent space is sometimes called as the manifold or the data manifold. Like how does the data look like? So what we have seen is, like, from different region in this manifold you can actually generate different type of images. And since it was very clear that, like, there are very distinct boundaries, you can actually use this to do some sort of a classification as well without any label. So what I have done is, like, I have certain images, right? I trained the autoencoder. I have seen that with the late with the manifold, I have seen that, like, there are different categories for different like images in this latent space. And it, so the question is, like, can you actually learn some sort of a classifier on top of that without using any labels? So only using the uh, unlabeled data, which is your images information, and this is some sort of unsupervised learning paradigm as well. So what we can actually extend it to, if you actually visualize this thing, you have three different clusters. So how do you actually visualize it? So there is something called as tsne plot. Since actually this is only two dimension, you can actually directly use scatter plot. But if your data is actually at a higher dimensional space, maybe suppose the latent vector dimension was 64, then you might want to downscale it to two-dimensional vector, and then you visualize that. So for that you have either PCA, principal component analysis, or TSNE, which is very famous. And if you actually look into sklearn library, these packages are there. So what I've done is I have visualized this like latent space for images, and you can see that, like, these are different clusters. So now I can actually use some sort of any clustering algorithm to do the visualization, and you can actually see what kind of performance you can get. So I mean, if you actually try, you should get actually better. But this was like, at least you should know actually what is the me center of this cluster. So if you know that at least what is the center of this cluster, then you should be able to map it better. But like there are like what do you say, unsupervised learning methods like KNN and GMM also. So you can use those methods. So I mean, like there are many applications, but like the gist here is like autoencode, for autoencoders you can actually use them for learning representations. You can use the representation in a different format. You can use them for image generation. This is a task of image generation, right, where I'm simply feeding in random values to the decoder, and decoder is actually generating sensible images for me. And the same task, or like the same thing actually continues in the latest methods, like whatever method you are using, maybe Gemini based models or anything else, right? Any question in this? Anyone, any doubt?
Sir, I have a question.
Yes.
See, there are different types of five with a different structure.
Yes.
If you see in the top, the structure of five is different. In the bottom, structure of five is different. If I want to generate the number of certain structure, for example, if I want to generate the other structure which is not present in the data set, is that possible? I mean, some handwritten kind of a structure.
Yeah, yeah. So question is,
No question. So the question is, how can I generate the high number which doesn't exist in the data set?
I mean, actually, whatever. So you will see that like you will not find out these like exact matches in the data set. So these are the generated examples, and if you actually look into the data set, right, you will, there are high chances you will not get this kind of five, right? You will get similar kind of five, but not the exact same. So since you are actually interpolating in the latent space, there are chances that like within the interpolation you will arrive at place which was not there in the original data set. Hence you are generating actually the new data. So what you can do is like just interpolate the whole data space, generate images, right, and add them into your original training data, train the model again, your maybe your classifier, and see if your classifier is actually able to do better now, right? If your classifier is actually able to do better, that means that the generated images are more robust, and you have uh, generated images that are very like not very close to whatever the existing like images were. So uh, so the controlled generation is very difficult. Like I only generate new samples which are not there in the dataset. That actually becomes very difficult. So one trick can be is that like you take any existing image, right? Get the latent representation, add some noise to that, and then try decoding it. So once you decode
Okay.
that, or decode that, you might get a slightly different version of that input image that you have given.
Okay.
Yeah.
But through vector, if I take the differentiation in terms of the vector, image vector or something like that, because why the structure of the uh, five which is in the bottom, which is different as compared to the five which is in the top, through some vector difference or something, is that
um,
possible?
Vector difference also you can take, but I mean, how do we actually ensure that like it's not there in the data set? So that is something which you have to take care of. So essentially what is happening here is your decoder is mapping everything to whatever it has learned, right? In the mapping you are able to get, because these are basically generated from noise only, right? And since we are generating from noise, we are able to get new samples, or like some, if you can see that like on the horizontal axis it might be there is a variation in the style of whatever you are writing, and in the maybe the vertical axis there is more of a style is similar, but the numbers are actually changing. So like if you actually do much better interpolation between along the horizontal axis, you will find out new styles as well. So this is basically called as the problem of disentanglement, where each word or each image has certain attributes. Suppose there is a face of a person, right? And there the face has many attributes. Nose is one of the attribute, eyes are one of the attribute, male or female is another attribute, smile is another attribute. If you can actually find out in which dimension the attribute is changing, then you can actually move along that dimension and change the attribute. Suppose you find out that the zeroth location, the attribute corresponds to what do you say, maybe the smile of the person. So if you actually start moving from like from suppose this point to this point along that first dimension, you can actually start to increase the smile of the person. So I mean this is a research topic actually, which is called as the disentanglement of attributes. So something interesting, and people are actually working on identifying that which vector actually correspond to which attribute. And since you are able to control how does the attribute change, you can actually control how does the generated images look like, or like you can actually have a very controlled generation.
Yes.
Yeah,
Thank you.
yeah. Anyone else? Any question? So there is some question. What will be the context vector change since there are two or different or more structure for single one? What will be the context vector changes since there are two or more different structures predicted from single one? I didn't get the question actually, but if you want actually you can unmute and speak up. Yeah, so yes, so the context vector is the hidden layer. Yes, that is true. And like since we are kind of interpolating, right? So if we actually look at the code, so what I'm doing here is for a grid, right? Between like 0.05 to 0.95, I am generating a x point and a y point, right? And basically sampling a point from a normal distribution at in a line space, right? And I'm using x and y point to feed it to the decoder, and decoder is basically generating the image for me. Since I'm since I'm actually feeding the random information, right? It is able to map. like how does that point of information which is coming in to a latent space. So you can actually see the whole grid, that like the left hand part actually corresponds to 0, center part corresponds to 5, and the like rightmost part corresponds to 1, right? So, and if you actually see along the horizontal axis, right, if I am changing this grid, you can see there is a change in the style of this x, of this one, right? It's like from like much more inclined to basically slightly straighter, right? So this style information was captured automatically in this variation autoencoder, and when we are basically we are simply exploiting this style information. You can see from the 5 also there are different ways of writing the 5, and since we are actually interpolating at different points, I am able to see how does this style is actually changing. So this style information was inherently captured in the variation autoencoder on, right, and we are basically simply exploiting that. And since it's a generative task, right, you can have multiple type of ones or multiple type of styles. It only depends on what random information you feed in. Great. uh, Anyone, any question? I just have one more application for this, and then when we can actually move to transformers. Okay, great. Yeah, so I mean the relevant part here is only, I'll just simply show you. So this is the like whatever we have seen, like it's very similar to that. uh, so what I have done here is I'm using this as a uh, like search mechanism. I'm using this latent vector as a search mechanism, right? So suppose I have a data point which is basically this query image which is 7, right? And I have a very big data set, and I want to identify or extract out images which are very similar to my query image, right? Suppose how does the Google search actually works? So suppose Google image search works, right? So suppose you upload an image, right, and it converts it into a query image, and it gives you all the images which are very similar to that your query image. So we can actually use this autoencoders in a form of this uh, like similarity based searching mechanism, right? So I have used this 7 as a query image, right, and I'll get the like latent representation for that. Within the dataset I have representation for other images as well, and I'll uh, pull the images that are very similar to my query image based on some distance. Distance can be anything, right? I mean, even the error, mean square error, or SSIM distance, or cosine similarity, whatever the distance can be, right? I'm just fetching out top 5 similarities or the distances, and you will see that like uh, all the images are actually like for query image you are getting the similar images, like only, right? even Even if you can see that like the structure is actually slightly different. So this is 4, this is much more sharper 4, this is much more curved 4. So right, so you can actually do store everything into the latent space, and while you are searching you can retrieve much more easily and faster, in a faster way. So mm, this is basically on different type of distance metric. You have Euclidean distance, Manhattan distance, Manobis distance, cosine similarity. So see, the 3 is actually a tricky part, right? In some cases I'm actually making error because the 8 is similar to 3, right? So this, in this case, there is error in retrieval as well. So I mean, like it also tells you what are the accuracy. So you'll have close to 96% of top 5 accuracy in term of fetching out the correct information. So so bottom line, or like the takeaway here is like you can actually use this like autoencoder in retrieval task as well. So in this case, the application is basically image retrieval. You have a query image and you want to search the closest images which are there in the data set, and like you can actually do like image based search as well, but that actually takes time. So a better way is you convert your image into an latent representation. For all the query or the candidate images, whatever they are in the data set, you store only the embedding part of them, right? And do a comparison in the embedding space. And if you, when you find out these are the closest images, you can pass them through a decoder and get the original image, whatever is required. Or maybe you can actually go to the image index and then just fetch it. So the search actually becomes very very fast. So uh, in case of real time application, maybe facial recognition task, right? Like where someone is trying to standing at the gate, and algorithm is actually running through thousands or millions of like possible candidate faces, then the time actually becomes very crucial. So these kind of tricks actually help in reducing the time. I hope it is clear. Sir, how much time it takes to train 200 epoch in this case? I mean, I think it should be done in 1 or 2 hours, because I was trying before this session and I could only train for maybe 60, 70 epochs in half an hour. So, yeah, maybe 1.5 hour should be enough on GPU. And since the data set is actually very easy and the model size is actually very limited, so uh, you can train things very fast. But for larger models, it takes time. Okay, coming back to the questions we were discussing. Okay, with regard to context vectors, vector based attention mechanism, right? Which of the following statement is true or like likely to be true, right? So alignment vector can be negative, but it is expected value over the distribution of hidden state is always positive. So if you actually like go back to the slides, so this is your alignment vector, right? And it is actually a softmax of whatever of your state, and so this previous state and your hidden states, right? So softmax is basically ranges between 0 to 1, so it cannot be negative, right? So this is a false, right? Second is in um, if the context vector ct does not consider connections from H T where K is greater than T, it may not it may not work well with as with those connections. So what it is saying that like what if we don't consider these connections, right? So what will happen here is like we do not have the complete context of whatever the input is, right? So suppose this is the task of image translation and you only see only the first maybe 10 sentences of Hindi, right? Then it becomes actually very difficult for you to translate it into English, right? So you should be able to actually uh, see the whole context, and like this context vector is actually kind of doing some sort of attention mechanism only to identify which words are more crucial for at that step for the translation. So this is correct actually. If the context vector CT does not consider connection from HT where K is greater than T, it may still work as well without the connections in the future input would depend on previous input. So uh, this is true that like the future input depends on previous. You get some context you get, but in many cases the context switches from where we started completely if there are certain words which like make a drastic change, right? So some maybe in term of sarcasm, like your like initial and your final sentence actually uh, differs, right? So you should actually have the whole context in order to understand what is happening in your source sentence. So such a mechanism can work for spatial temporal data such as videos. So this is true, right? So this is a temporal mechanism, right? Like where you have words which are coming in at each time step. Similarly, instead of words you can actually have frames. So this is frame 1 f1, this is frame 2, this is frame 3, right? And you can actually get a context of all the frame what is happening in suppose first 20 frames, right? And then at using those 20 frame you are basically doing some sort of maybe activity prediction that what is happening inside the video, or maybe next frame prediction, or maybe suppose someone gives you like just initial video of maybe 5-10 frames and tells you that complete the video. So then it becomes a generation task, right? So you should have the context of all the 15-20 frames, right? And then you should basically start generating, and for generation you should have previous information context vector, and then you should basically start to generate whatever the context it. So so the same task is actually can be extended to spatial temporal data, right, such as in videos. Which of the following statements are false? So using attention based image captioning technique helps better explain the failure compared to the legacy techniques, as the caption get generated word by word, right? So so attention based method is actually better, right? uh, so this is not false because in when you're doing actually the image captioning, so you might have seen that like there are different words and you get to see that how word is basically correlated with the image, right? So and it gives much better understanding as well as mapping that which part of the image the model is actually focusing to create this caption. Next is the decoder of the visual dialogue cannot be truly deterministic as it involves computing the maximum likelihood of correct option. uh, Visual dialogue system cannot be truly discriminative. I think this is false. Recorded of the visual system cannot be truly discriminative. No, it can be discriminative, right? Like there are a set of vocabulary, and you are basically picking out um, to which word like you are basically predicting, right? So it is in a form discriminative. Blue score uh, is always between 1 to minus 1 to a, so actually blue score is basically between 0 to 1. So just to give you context, what is blue score? So um, in image, so it started in like translation task. So where you have suppose French or maybe Hindi to English translation, right? So what is happening here is like you have maybe uh, so you say mera naam, something like that, right? And my name, whatever it is, right? So like it works. So there can be multiple candidates, like my name, I am, like I am Ayush, right? Like, or like say my name is this one, right? So how do you actually say that, like which one is actually better and which one is like slightly not completely wrong, but um, like there has to be some sort of a scoring mechanism, right? And blue actually does that. So um, you have this is the generated response, and you have the human reference as well, right? And so if the human reference is the correct is my name is Ayush, right? So what you do is you identify how many words are basically correctly matching unigrams, right? So in you just say you unigram match, right? So suppose there are four possible words which should be there, and the correct all of the four words are present, then it becomes 4 by 4, and the score actually becomes 1, right? If none of the none of the word matches, so suppose I am maybe Taj Mahal, right? So if none of them matches, it becomes 0 by 4, right? So the score actually becomes 0. So sorry about that. So what happen is in some cases for this like only the name is actually correct. So your 1 by maybe 4, something like that, right? uh, so what was the issue in this case, that like if you're actually checking for word, so suppose I only predict Ayush, right? All four Ayush, so it becomes basically 4 by 4. So Ayush is actually present in like the original human reference, and I just checked that. So like for this, people actually start to use this clip of words, right? Like there has to be a unique correspondence and no duplication of the words. Then there was to do things much better. People use bigram. So bigram is basically pair of two. So suppose my name is present, my name is present, right? So uh, in this case, it becomes like maybe 1, right? So because my name is present in the human reference, my name is present in the generated reference, right? But in this case, in second case, there is no my name is present, right? So it becomes 0 by actually whatever the number of bigrams which are possible, right? Number of bigram, right? In this case also it becomes 0, 0 by number of bigram. Then third become trigram. They check for pair of three words. So my uh, name is Ayush, like, right? Something like this. Okay, so if my name is present, then it becomes 1. My name is Ayush is also present, then it becomes 2. So the score is actually 1 in this case. Right, in this case, my name is not present. Name is Ayush, that is also not present, then score is 0 in this case. And here also it is 0. Right, and there is one more factor which actually um, um, mm, like influence it, that is the size or the length of generated sequence. So what people generally want is it has to be similar, the length of uh, generated should be very close to whatever the length is for the human reference, right? So this has to be very close. So it should not be the case that like we have the original human reference is a long sentence and we are basically generating a very small sentence, and the other way around is also true, right? Like, so the original human reference is very small sentence, maybe 5 words, right? And we have generated like suppose 10 words or 15 words sentence, and these 5 words are actually present in this 15 words. So there are chances that it might boost the your blue score. So uh, it checks for word, it checks for word pair as well, right? It checks for length as well. So these are the three parameters which blue score actually works. So blue score uh, is one of the initial metrics where people started using, but there were few flaws in the blue score as well, like it doesn't work well for images which has variable length translations, maybe Hindi in English, French to English, right? Like for English language it worked fine, but for other language there are certain flaws people identified later. So yeah, it's a good read if you want. And so Hugging Face has inbuilt blue score as well. BLEU, I guess is the name. So you can actually directly use blue score. Um, uh, like yeah, it's already inbuilt in the library. So next is, which of the following statement is true for transformer? So vision transformer does not require position uh, encoding, as they are temporal, as they are not temporal data. So vision transformer, what vision transformer does is, suppose you have an image, it slices the whole image into different tiles, and each tile works as a token, right? So they simply flatten out the whole image into this form, right? And each tile is basically a token, and each for each token you have a embedding represent, you have embedding, right? So how do you know that, like since we have only simply flattened out the tiles or patches, how do you know at what place this patch was? So in order to get the localization information, we use this positional embedding. So suppose you have additional positional embedding here, where you're basically telling that like this was 1 comma 1 patch, this was 1 comma 2 patch, this was 1 comma 3 patch, and like yeah, this is maybe last 3 comma 3 patch, right? So that patch information or localization information is essential, right? So whenever you pass these things to transformer, they should actually have a sense that like how patches are related, how objects are related to the patches. So since it's a transformer like architecture, you do a self attention, right? So you will see that like the structures like maybe suppose there was this, maybe this structure was there, then 1 1 1 2 2 1 2 2 and 3 1 patches are actually responsible for the structure, right? So this information need to be passed into the transformer, and in vision transformer they require actually like the positional embedding. So this is actually wrong. So next is input data is parallelly passed to all stacked encoder in the transformer. This is actually wrong. So it's basically passed to in a sequential manner. uh, Input data is parallelly passed to all stacked decoder in the last layer. This is true. So that is why you need a masking mechanism, right? Like so that whatever the data coming in, we only see the uh, like what you have a mask, right? Like 1 0 0 0 0. We only see this times this token basically, which is the starting token, and then you have information which is coming in from the encoder, and you start to generate based on that, right? The weight value of each QKV matrix of the multiple head of first encoder of the single transformer kept exactly same. So like in case of multi-head attention, the whole thing works because you initialize k q v of different heads in a random manner, right? So when you initialize them in the random manner, what happen is like they start to learn out different things, and it actually becomes some sort of an ensembling mechanism where different heads are learning different kind of correlations between the data, and actually helping the your next linear layer where you are passing on the whole concatenated data. So this is also. So only C is was the correct one, right? So next question is, consider the standard attention mechanism for a single head given by softmax, right? So you have a stand q k transpose square root of d, right? And this is softmax, and it is multiplied by v, right? So what question here is, like suppose the entries of q is multiplied with a scalar x, and entries of k is multiplied with scalar y, right? Then upward arrow denotes the event that all the modified softmax probabilities will become uniform. So this basically tells you that like the softmax probabilities become uniform, right? So what is basically softmax? So it's some sort of this distribution, right? And much the sharper it is, it is better for us because you know that like only one instance has a very high probability, and everything so the sum is actually like the range is actually between 0 and 1, and the sum is actually 1. So it's a basically a true form of a probability distribution, right? um, Downward arrow actually like makes it away from like uniform. Let's say it is sharp, right? Like something very sharp, and then just like that. So say that like at this place the probability is very high and the rest is zero. So this is the ideal case for us, and this actually means that there is no change, right? So let us denote this as logit by some character L, right? And what we are doing here is there are two numbers x and y and multiplying it with uh, basically q and k, right? So the takeaway here is, suppose uh, q and k sorry x and y is basically very small values, right? If the x and y are very small values, that means that like the whole value actually becomes this L, uh, suppose x y L, right? If x y is less than 1, right, then this whole term actually become closer to 0. Then if it becomes closer to 0, then it goes toward a uniform distribution, right? So if x and y, the product of x and y is less than 1, then it becomes a it goes closer to the uniform distribution. If product of x and y is equal to 1, then there is no change, right? So uh, it remains same. If x and y is basically greater than 1, then it becomes very sharp. So suppose like you have values maybe 10, 20, 30, and you have other values like mm, maybe 20, 30, 30, 50, something like that, and then you're multiplying everything into maybe 100, right? So if the value is very high, right? So suppose the multiplication earlier was multiplication was 10, 60, maybe 150, something like that, and now I'm multiplying everything into with 100, then actually the gap becomes very very large, right? So when you're basically multiplying with value greater than 100, sorry, greater than 1, then it kind of enhance the gap which was there in already there in the samples. So this becomes maybe 2000, this becomes 6000, then it's become maybe 1,50,000, something like that. Sorry, 15,000. Yeah. So yeah, so the gap actually becomes much larger and it becomes much more steeper, right? Something like that. So only so the takeaway here is this part actually. Takeaway is this part. So you need to see how does the xy values pan out, and you will be able to correlate with like how does uh, the softmax changes. So first option was you have log 2, square root of log 2 into log 2, so it becomes log 2, it becomes 0.63, which is less than 1, so it makes things closer to the uniform distribution. Second option is basically you have a 2 comma 0, right? So the product is basically xy product is 0, less than 0, so it makes things closer to the normal distribution, or sorry, uniform. Third is zero point 0.5 and 2.2, the product will become 1.1, then it is greater than 1, then it moves it makes things much more sharper. uh, Finally, this is 10 into 0 0.1, it becomes 1, that is equal to 1, right? So then it is no change, This is 8 into 0.124. It is 0.99 less than 1. Then less than 1 is basically taking it closer to the normal distribution, right? So the takeaway here is, just check what is the product of x and y is. If it is greater than 1, then it is making things much more sharper. If the product is less than 1, then it is basically making things uniform. If product is actually equal to 1, then there is no change. So the last problem is actually consider the positional embedding mechanism and describe in the attention is all unit people. So Pij denotes the value of entries in jth row and the ith row and jth column in the positional uh, decoding. So like, so your positional embedding is actually looks like this. So you have, suppose your dimension of your positional embedding is maybe suppose 64 or maybe 512, right? And you have the vocabulary size of suppose 100. So for each word you have a positional embedding of 512 dimension, right? And basically it is given by this formulation. So for whatever the position is, you have a sinusoidal component and you have a cosine component. So this is sine and this is cosine part of it. And what we want is like, so there are different type of m's which are given to us, m and n. And what the question is asking is, what is the value, at what value Pij is equal to uh, Pi comma 2j is equal to P positional embedding of m comma 2n. So at, so we want to identify at what, uh, in what cases this is true. So let us say the first one is like the m is equal to 100 I, n minus j is equal to d dimension of embedding by 4. So uh, right, if you actually see, this is how you can write this. This is how you can write this: I by 1000 to the power 2j by uh, d dimension d embedding is equal to m uh, 10,000 to the power 2n by d embedding, right? So what we do is like m is equal to 100j 100I, n minus j is equal to d embedding by 4, right? And simply what we'll do is like simply replace this in this, right? So this is 100I and 10,000 uh, 10,000 to the power 2 n. We are saying n is equal to j plus d embed by 4, right? And just simply replacing n by this, right? And you have a division by d embedding dimension of embedding, right? 100, what we'll do is like there's a plus term, so in term of power it actually becomes a multiplication term. So you have first term which is 10,000 to the power 2 j by d embedding. Then you have 10,000 to the power of 2 into uh, d embedding by 4, right? And there is a d embedding in denominator as well. So this d and this d embedding cuts down, it boils down to 1 by 2, right? So basically we're computing the square root of this. This becomes 100, it get cancelled by this, so it actually becomes I by 10,000 2j by d embedding. Similarly, uh, similarly we can actually try for the other cases as well. So you have suppose 10 m is equal to I, so I is equal to m is equal to I by 10, right? So in this equation, like suppose let's say this is 1, I'm replacing whatever the value I'm getting for this, right? So I by 10 I'm using this. You have 10,000 to the power 2 j minus uh, d by 8 by d, right? So in this case, what was our second case? What is j minus n is equal to d by 8? So n is equal to j minus d by 8. So right, let us say this is 2. I'm putting this here, right? So I by 10, uh, this actually like becomes the, like we have seen this earlier as well. This is very similar to whatever we have seen here also, right? Since it was negative, I have taken it in the denominator, right? D cancels with D, right? And you have a 2 which cancels 8, it becomes 4. So it boils down to 1 by 4, becomes 10, right? This cancels this, and it becomes this one, right? You can actually try with other ones, other as well, but like I think first and second is correct. Okay, so I just want to give a walkthrough of how does the transformer architecture look like. So we will try and implement each block, right? And if you have any question, just ask. Right, so you have like you are actually doing a suppose a translation task. You have hello, like you have a word which is in which is in English, and you have a sentence which is in French, I guess, right? And what the objective is to do some sort of a machine translation task. So transformers have the first part is basically tokenization and embedding generation. For each word, you assign embedding to it, right? For each word, along with embedding, you add the positional encoding to it, right? So that like you understand at what location the embedding is placed, and it will have the sequential information embedded into itself, right? Then you have multi-head attention. So you do like all same operation, but like in the parallelly you are actually doing the same operation, right? And then you concatenate everything into one like output, feed it to the linear layer, and do some normalization, right? And just pass it to the next layer, right? So this is your encoder block. In the decoder block, you have an input which is coming. You have masked multi-head attention. Masked in the sense that like you don't want to uh, like see the other words, right? So first word is suppose bonjour. You just want to focus on the first word, and do not basically cheat and see that like what will be the next word. So based on this first word, you want to predict what will be the next word, and for that you get context information from the encoder, so in form of key and queries. And you'll have your own values from which is coming in from your start token or maybe the first word. um, you like for each you represent query keys and values by matrix in the matrix form, right? And you multiply your input embedding with these metrics to get q, k, v. And the attention mechanism, which is very common, is basically this: you take the softmax of q and transpose of k divided by the dimension of your I guess query vector, and you multiply it with the value, so that like now you have uh, a sense of how each word is important to you, right? So this is the overall flow. Let us see how does each uh, like parts pan out. And there is this J. Alamar blogs, which is very famous, and like a very good explanation they have given. So I think it is very good read if you have some time. So basically, there are two parts. You have encoder block, you have a decoder block. You take some input and you want to translate it into some other language. So maybe French to English translation is there. Right, so first task here is you initialize your embedding. So in this case what I've done is like we have initialized the embedding to 512 dimension, right? So each embedding is of 512 length. So and each embedding is representing a word in the dictionary. So suppose there are 100 words in the dictionary, so your embedding matrix actually becomes 100 cross 512. So that is, if you actually use nn dot embedding, your vocabulary size is basically 100 and your embedding dimension is 512. So your embedding matrix actually becomes uh, your 100 cross 512. Whenever a word comes, suppose say hello, it will actually go to the index of hello, right? And just take the embedding and pass it to like your transformer during like the inference time. So embeddings are learnable, right? You can actually use some, in some cases people use pre-trained embeddings as well. But like if you have sufficiently large data, you can actually learn them as well, right? And suppose like you have a batch size of 32, and uh, each instance has a like suppose 10 words. Your data becomes 32 cross 10 cross 512, right? Similarly, like with input embedding, you provide positional information as well. So the positional like the positional encoding matrix and your like original embedding matrix have the same dimension, that is sequence length into whatever is the embedding dimension you have decided. So for each word you like you have a positional information along with that, so you simply add it to your embedding vector. So this is like the code for generating positional embedding. So you have sinusoidal part, you have a cosine part, and you are basically adding them. So next is your self attention module, right? So like in the self attention, you attend to all the part of your sentence. Then there are basically multi-head self attention as well, where you have multiple heads. Suppose there are 8 heads, and each will be doing the similar computation for each sentence, right? So what uh, uh, so what you do is like you resize your 512 dimensional embedding into 32 cross 10 cross 8 cross 64, right? So 64 was your key query vector dimension, and if you multiply 8 into 64, it becomes 512 actually. So like you split it into 8 different parts, and this 8 is actually telling you that like there is 8 multiple heads which are computing your key value attention, and you basically concatenate everything into one vector and then pass it to the linear layer after this, right? So you can calculate your score, multiply. So you do the multiplication between q and k, right? So suppose your input is basically so query and key have the dimension of 32 cross 10 cross 8 cross 64. 32 is your batch size, 10 is your number of words in a sequence, 8 is number of heads, right? And 64 is the dimension of uh, your query matrix, right? And like if you do the multiplication, it actually becomes 32 cross 8 cross 10 cross 10. So if so what I've done is like I've just swapped this number of heads in front, and then this becomes 32 cross 8 cross 10 cross 64. This becomes 32 cross 8 cross 64 cross 10, right? And if you multiply them, it becomes 32 cross 8 cross 10 cross 10. You do the normalization, you multiply this with your value matrix, and if you can see, you will get the output in the form of this 32 cross 8 cross 10 cross 64, right? uh, and then you concatenate it through all the 8 heads, right? And your output shape actually become 32 cross 10 cross 512. This output you pass it to your next layer, right? So this is the code for multi-head attention, right? You have embedding dimension, which is 512. You have number of heads, which is 8, right? You divide the number of heads, uh, your embedding dimension with number of heads to get what should be the size of each key query value embedding, right? And you basically define like query metrics, key metrics, value metrics, so that like the computation actually becomes easier, right? uh, Whatever the operation we have seen above, we are basically doing the same operation here, right? You have uh, key value, you have these metrics which are defined here. You are doing the multiplication, like so score is should be this product single head. Yeah, so this product is actually coming from matrix multiplication between query and k, right? And it should you should get output of 32 cross 8 cross 10 cross 10. This you multiply with your value. Now you get the corresponding attention on that for that sequence, right? And what you do is like you multiply uh, this number of heads, basically concatenate this number of heads, and your output actually become 32 cross 10 cross 512, right? So just transpose this here, and you just multiply 8 into 64, right? Right, this is the output of this layer, add and norm, right? Multi-head attention plus add and norm. Now you have a feed forward layer which basically take this 512 and map it to maybe 1024, something like that, and then pass it to, so yeah, that's what it does, like 32 cross 10 cross 512, map it to 2048, then again back to the same dimension 512. So yeah, so the transformer block actually has multi-head attention, you have layer normalization, you have a feed forward part where you have a linear layer, right? You do the expansion, and then you put the embedding back to the original embedding space, right? uh, and the transformer encoder has multiple such instances. So like this module list actually initialize the same thing multiple times, and this number of layer parameter, which is 2 in this case, decides how many times you are basically repeating the same step. So your encoder, like this transformer encoder has multiple such encoder blocks, like this transformer blocks, and these are basically extracting out your information. In the decoder part, you are taking your like giving the context from your encoder to the decoder, right? And you have like the output, you have them like whatever the maybe the start token, right? You start with that positional embedding, add the positional embedding, and then start to generate whatever the next word you are predicting. So it also has multi-head attention, but it is a mask multi-head attention. We will see that. Uh, so this is the mask multi-head attention. So this is the mask we are creating. So suppose you have a sequence length of 5. In the first instance, only one will first sequence will be visible. At second time step, only first and second will be visible. Then you have the first three will be visible, then four, and then five, right? And what we will do generally is for creating mask, we'll use 1e like 1e minus 20, right? Something like that, so that the value is actually very close to 0 but not exactly 0, so that like there should not be any overflow with division by 0 kind of a problem, right? uh, then decoder block is actually very similar to what was the like encoder block. You have multi-head attention, you have layer norms, you have transformer blocks, and similarly you can actually have multiple decoder blocks as well, right? Yeah, suppose you have a vocabulary size of 11. You have target vocabulary size which is also 11. So target and source are basically will be different based on from which language to which language you are translating, right? Number of layers you can define. What is the sequence length? Maybe in this case this is 12, right? And so words actually you map it to tokens and you assign certain number to it, right? So 0 is basically the start of sentence, 1 is basically the end of sentence, right? In this case I'm defining two words here, two sentences here. This indicate start of sentence, this indicate end of sentence, and similarly you have the similar uh, tokens for your output like language as well. So you have a start token, end token, and like you have different token assignments for different words, right? And if you actually just see that like you have embedding dimension 5 and 12 vocabulary size, it will create a architecture for you, right? Like, so there are 6 transformer modules. We have said that like a total number of layers should be 6, right? You have multi-head attention, whatnot, whatever we have defined. Similarly, you have embedding dimension of 5 and 12, vocabulary size of 11, right? Similarly, 6 decoder blocks as well. And if you simply output it, you should get like the response for that, right? So um like now it's actually predicting all basically all zeros because it's not trained there, but once you train it, it should be able to predict the responses correctly. So the whole intention is basically to get a sense of like dimensions and how does each metrics and input are structured so that like you can have architecture end to end. So uh, so this is what I have for today, and if you want, you can actually ask any doubt. And what we'll do is like we'll share this resources with you. You run it and see you understand it. And my suggestion is like just do a pen paper kind of computation so that things are actually clear to you. So I myself, when I was studying about it, I do all the matrix multiplication by hand and to see that what should be the output dimension of this, so that like you have a sense that what is happening. So why like embedding dimension is 512, your key query dimension is basically 64. Those kind of understandings should is required. So it is good exercise to actually do a pen paper based like computation analysis. So there are let me just so this is a Hugging Face library. Like when you are training transformer or some similar architectures, they are basically the leaders in basically documentation, or they have all the models as well. So uh, like you can actually take a look into this. How does the trainer like API looks like, right? uh, and they have made things like very simple, so you should be able to find like get blogs on how do you actually train transformers, uh, right? So very simple, load data set, you have pre-trained data set as well, you define BERT. So there was uh, architectures, BERT architecture, you can use the tokenizer for that. Like there are videos as well, right? So just go through them. I'll just put it into the chat, and you should be able to uh, get started with training these transformers. People have trained it for different application in the medical applications like report generation, or uh, like question answering with the doctor. So in case of emergency, right, you want to um, like communicate with doctor that like I have this issue, what should be the case. It should be able to give you some sort of decent like responses. So there are many applications. I think like start playing around with it. Just get a data set and see like because it is a good exercise, and also it's very tedious process as well. So once you get data, it has lot of issues. You need to structure it well, right? You need to remove all the unwanted things from the data set, and then uh, train your architecture. So that like from raw to trainable format information or data, itself is a big pipeline. So um, for starting, just take any clean data to just train a transformer architecture and see if you are able to get the prediction. For getting like the real world application, uh, see if you can actually get any data, maybe get few of the papers from of on one topic, and make it um, like expert in that region, or maybe get news from all the, maybe from Chinese columns, or maybe American newspapers, train it, um, and that like, so that like now it is good. In fact, maybe get the Wikipedia data, and just train a fact checking bot which should be able to get uh, the facts right. So yeah, there are many applications. So I mean, it's up to you, like on how you are actually going to exploit it. So yeah, any questions on this? We have some time. If anyone has some questions, any question, uh, good time to ask. Okay. Sir, how do you develop intuition in building these kind of models? Your project struggle to correlate deeply. So I think get the basics right, I guess. Like try running things which are already pre-existent, and then see if you understand each component of the problem or the architecture. So like the intuition actually builds from very low level to high level. So like if you actually know right how things work internally, you can actually correlate things into different dimension. So the suggestion would be to like write your own code, understand those codes, try with dummy data, play with dummy data, or just see if you can actually make things run which are already there. Someone is creating it, like file or like maybe a small project for that. Then start to correlate things, right? Suppose you have trained a model for maybe uh, maybe for generating new news or like anything, right? Like suppose then something comes up to your mind, right? Like and see which part of already learned examples you can actually closely associate with it. So maybe someone say that like can you actually uh, like create a model which uh, maybe create a website for you, right? And or maybe just tell you how does the alignment of different components should be, right? So like just see that like how you are able to connect with whatever you have already learned. So it's a generative task. Yeah, it's a generative task. So like see if you can actually get these text based generation model to give you a layout, right? So just get the basics right, uh, apply them to already well formed problems, understand them, and then you will slowly start to see that like the many problems can be actually bend in the similar category, if not, right? So yeah. Anything else? I hope I answered your question. Anyone else, any question? Okay, then we will close it here. Uh, yeah, thanks everyone for joining. You can actually post your questions in the discussion channel, and like you can actually bring in your doubts in the next session as well. So yeah, just I've shared already shared this VAE file. Just try running it, and this I'll share the other file as well, which is for the transformer. So this should be able to run it. Okay, then we'll close it here. Okay. Thanks everyone for joining. Bye. Have a great weekend. Bye.